Okay, our next lesson is on atomic notation and isotopes. Yesterday we talked about atomic theory, and we talked about the different pieces of the atom. We talked about Thomson and how he put the electron into the atom. And we talked about Rutherford and how he used alpha particles to fire them at gold foil, and some of them came back and discovered the small positive nucleus of the atom. We talked about neutrons and how they're neutral, also found in the nucleus. And with that, we can now start talking about how we represent atoms in terms of those different particles, and another important thing called isotopes. Okay, so first we want to talk about some important numbers that we find in defining atoms, and that is the atomic number. And so if we wanted to represent an atom in terms of its basic parts, protons and neutrons and electrons, we need certain values that kind of represent these different pieces. And so the first one is the atomic number, and I'm sure you would have done this in grade 10. So the atomic number, we give the symbol Z. I don't know the historical reference on why Z was used. You'd think A, but it's not, it's Z. And it tells us the number of protons present in the nucleus of a particular element. And if the atom is neutral, remember, an electron's charge completely balances out a proton's charge. So if the atom is neutral, then it has the same number of protons and electrons in that atom, all right? And it turns out that this atomic number tells us the identity of an element as well, all right? So if we were to maybe go to the internet here, again, and if we were to do a quick search on the periodic table, and we have a periodic table up in the room, but I'm not in my room right now. So if we take a look at the periodic table here, we've got all kinds of great options here. Let's take a look at this black and white one here. And it's not coming in very clear. That's no fun. Here, let's bring this whole thing up. View the original image. Okay, here we go. So here we got a periodic table. It's kind of a neat one. It's a little bit of an interactive one. So if I take a look at this hydrogen atom, all right, don't mind the advertisement. If I take a look at this hydrogen atom, it has an atomic number of 1. All right, there it is. Z is equal to 1. But if I know that that Z is 1, then I know that the atom is hydrogen. So the number of protons and the atomic number mean the same thing, and the identity of the atom is determined by that. So I can get actually 3 pieces of information from the atomic number. I can get the atomic number, 1. I can get the number of protons, 1. And I can get the identity of the atom, hydrogen. So I can pick any other spot. I can pick here phosphorus. So if I pick, if I pick phosphorus, then I have an atomic number of 15. It locates it on the periodic table. I know there's 15 protons, and I know that I'm dealing with phosphorus. So I could ask you any of those pieces of information, like if I were to say, what element has 30 protons, right? You go to 30 here. Oh, zinc. And what's the atomic number? Oh, 30, because it all means the same thing, all right? So the atomic number, Z, tells us the number of protons and tells us the identity of the element. All 3 things are found in that bit of information. Okay, the next thing is the mass number. So the mass number, which is silly because they call it A, again, I have no idea. It's a backwards thing, but that's the way it's done. The mass number tells us the mass of the atom. And the mass of the atom is determined by the number of protons plus the number of neutrons. You might ask, what about the electrons? But if you remember back to our last lesson, the mass of an electron is like 1/2000th, okay? 1/2000th of a proton. That means you would need 2,000 electrons in order to have the mass of 1 proton. So we don't worry about the number of electrons that are there because their mass is so tiny. So the mass number is simply the protons plus the neutrons. All right? Now, if I don't know the neutrons, I could rearrange this equation here, and I will do that for you. So let's say I want to find the number of neutrons. I need to bring the number of protons over to the other side, which means I would need to take the mass number. I would bring this to the other side. We're going to do some simple algebra here, minus the number of protons, and that's going to get me the number of neutrons. So very simply, I can get the number of neutrons by taking the mass number, the total mass, minus the protons, so that whatever's left is my number of neutrons. I can think of this in terms of then mass number and atomic number. So if I know the mass number and I know the atomic number, I can always subtract and get the number of neutrons. So here's a good one right there. Whoops, that was horrendous. Let's see if I can fix that. No, I'm not going to. And number of neutrons is equal to the mass number minus the atomic number, which is the number of protons. We'll do some practice problems on that in a moment or two. So standard atomic notation, all right? When you do the PowerPoint, I am going to want you to write this down. You don't need to necessarily write down mass number, you could put here, you know, n, z plus n, all right? With this one here, excuse me, right? Here you can put the atomic number, number of protons, right? Yeah, no, I would just define this as mass number and atomic number, right? Number of protons. Here we've got a couple of examples. Again, write the examples down, please, when you do the note. And so here we've got a mass number of 12 for carbon and an atomic number of 6 for carbon. And here you can see here I've got a different type of carbon. This carbon has 14 as the mass number, and of course 6 is the atomic number. And that's because, and now I'm introducing you to a new concept, it turns out that even atoms of the same element, the same identity, can have different number of neutrons. If I wanted to figure out the number of neutrons here, all right, again, I would take my mass number, Z, minus the atomic number, A, and in this case, I would take my 12 minus 6, always the big number minus the small number, and I would get 6. I would get 6 neutrons. And in this particular version of carbon, I would take, to determine the number of neutrons, I would take my 14 minus 6, and I would get 8 neutrons. And that means that this version of carbon has 2 extra neutrons than this version of carbon. And that's okay. It doesn't affect the chemistry because chemistry is dependent on the number of protons, on the identity of the element. And it just means that this carbon is a little heavier than this carbon. All right, it's got 2 units more. And it turns out that when we have 2 elements of the same type that have different mass numbers, we call them isotopes. I'm going to explain to you in a moment why we call them isotopes. Let's take a look down here at the bottom. Our 2 isotopes can also be written in 2 different ways. Instead of writing it in this fashion, all right, here's number 1. Here's number 1 way in which we can write something down. We can write it down like this, right? This is C12. C, we know, stands for carbon, and 12 is the mass number, okay? And so if somebody says C12, you can determine how many protons there are because I can go to a periodic table, all right? I can see that carbon has 6 right there, so I can get all my information. And 12 tells me the mass number, which means I could subtract and get my 6 right there. Another way of writing it is carbon 12. This is something you might see in a newspaper article because not everybody knows what C is. So if someone were to talk about, you know, in a news article about, say, carbon 12, they would write carbon 12, all right? And hopefully now you know that the carbon obviously stands for carbon, and 12 stands for the mass number. So our other isotope can be written as C14 or carbon 14, all right? So let's keep going. We'll do a couple of examples here. So let's say we have a potassium atom, excuse me, and it contains 19 protons and 20 neutrons. Determine the atomic number. So Z, the atomic number, that's equal to the number of protons. The atomic number is 19, all right? And the mass number, A, The mass number, remember, is the number of protons and the number of neutrons. And in this case, it's 19 plus 20, which is 39. Write the symbol for this potassium atom in 3 different ways. Well, the first one, potassium, and then the first one had, right, the mass number, 39, the big number on the top, the little number on the bottom, 19. It could be written as K19, or it could be written as the name potassium. Oops, lost an I. Potassium 19. Whoa, I made a mistake. That's 39. I need the mass number on there. 39, right? The mass number goes in the end. The mass number. All right? Okay. So that's how we can write these guys down. So let's write some definition now for this idea of isotopes. Isotopes are atoms of an element which have the same number of protons and electrons if it's neutral, but different numbers of neutrons in the nucleus. That's one way of thinking of it. Protons and neutrons, right? Same protons, different neutrons. Another way of thinking of it is atoms of the same element that have the same atomic number, but different mass numbers, all right? Now, we've already talked in terms of different types of definitions. Because protons and neutrons cannot be seen, this is a theoretical, ooh, that's a horrendous spelling. Let's fix that. This is a theoretical definition, theoretical, and I changed the color. Who knows why? Theoretical definition. And this one, and it turns out that scientists can experimentally measure the atomic number and the mass numbers. All right, I won't go into detail on it, but they can. So this is an empirical, I don't know why I did this, empirical definition. All right, so same number of protons, different number of neutrons, same atomic number, different mass number. Okay. Hydrogen has 3 different isotopes. Write this down as an example, but there's hydrogen 1 with 1 proton, that's it. And most of hydrogen in the universe is found in this form. There's hydrogen 2, and it's so important, it gets its own name, deuterium. It has 1 proton and 1 neutron, mass of 2. And there's a third type, and it is tritium, and it has 1 proton and 2 neutrons, all right? Both 1 and 2 are naturally occurring, all right? This occurs in nature, and this is not naturally occurring, but it can be made in things like nuclear reactors, and again, it is radioactive. Radioactive, all right? Danger, I don't know if I could draw a radioactive sign. Oh no, I'd give it up. Give up the radioactive sign. All right, so you'll write those down when you get to the note. Okay, since isotopes of an element contain the same number of protons, they have the same chemical properties, so chemically they behave the same, and isotopes of an element, though, have different physical properties. Their masses are different, okay? A little bit of a story I could tell on this. Yeah, no, I won't do that now. Okay, so on your worksheet, at this point, you can do isotopes and average atomic mass questions 1 and 2. So when the supply teacher hands that out, you can work on that. But first, though, I want to do one last thing, and that's talk about relative atomic mass. We'll do some example problems, and then you'll be good to go. So we've been talking about masses of atoms in terms of this unit right here, U, all right? Last day I talked about the fact that a proton, right, has a mass of 1 U, and a neutron, sorry, charge 0, has a mass of 1 U. And the question is, what is this U, all right? The relative atomic mass of an atom on a scale which has the mass of one atom of carbon-12 is exactly 12. I need to. So the unified atomic mass unit, U, is the unit of mass for atoms, and it is exactly 1/12 the mass of a carbon atom. And we can actually weigh that. We now know it's equal to 1.66 times 10 to the minus 24, phenomenally small mass, all right? And don't worry about that number. We may use it in the future. We're not going to use it right away, but it's just that, you know, protons and neutrons are not very heavy. They're quite light. So the average atomic mass, a weighted average of the masses of all the isotopes of a particular element. If we go back to our periodic table here, all right, let's take a look. You'll notice that all of our masses, all right, have these decimals, and I talked about that. And so these decimals, where do they come from? Well, they come from the fact that there's isotopes, all right? There's all kinds of isotopes going on here. Here we've got beryllium. It's got a number that is definitely not a nice whole number. Even carbon, right? So what does this mass mean? This mass is what we call a weighted average, okay? And a weighted average takes into account how many carbon-12s there are and how many carbon-14s there are, okay? Here we've even got a table of isotopes. This is kind of neat. I didn't see that. What are the different isotopes? How does it tell me the isotopes? Anyway, let's keep going here. Okay, so let's do some calculations here. So how do we calculate then what the average atomic mass is? Natural chlorine contains two isotopes, chlorine 35, mass of 35, and chlorine 37. There are no 36s for chlorine. And 75.53% of the atoms are carbon 35, and 24.47% of the atoms are chlorine 37. Calculate the average atomic mass of chlorine. Okay, so here's how we do this. Normally I would do an example with you to kind of hammer this home, where we talk about the average age of the student in the classroom. Obviously I'm not there, so I can't do that. But if you think it through, you know, if we've got a lot more 35-year-olds, which we don't, but 35-year-olds in the classroom, right? 75% of the classroom is 35-year-olds. And if we've got a lot less 37-year-olds, 24% of the classroom is 37-year-olds, then the mass, the average mass, or average age, whatever you say, has got to be closer to 35. Because there's 75% of the class, right? The average of the two numbers is 36, but that's if we had 50-50, and we don't. We've got 75-24. So we need to take into account these percentages when determining the average atomic mass. And here's how we do this. Here, let's first write down an equation. Average atomic mass is equal to, okay? And it's going to be equal to the atomic mass of the isotope, right? And that's A, right? The atomic mass of isotope A, all right? Times the percentage divided by 100, because we want to turn it into a decimal, for A, plus the atomic mass, or the mass number, sorry, of B times the percentage divided by 100 for B. And if there was a C, there could have been another isotope, the atomic mass of C, and its percentage divided by 100 of C. And I'm going to put a dot, 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 because it depends if there's more isotopes or not. So in this case, 35. The mass is 35U. And its percentage is 75.53. We're going to divide it by 100 so we can turn it into a decimal. 37 U, 24.47 over 100, turn into a decimal. And that's all the isotopes we have. So now we're going to pause for calculation. 35 times 75 divided by 100. That first number is equal to 26.44. 37 times 24.47 divided by 100. That second piece is 9.05. So what does this mean? It means that the 75% of the isotope, that is 35, contributes to 26 mass units of the mass. The 37 contributes to 9.05 mass units. Add them together, 26.44, and I get 35.49 U. And that's the number we see on the periodic table. The number we see on the periodic table is the weighted average of all of the isotopes added together. All right? And so that's how you determine the average atomic mass. And you can now finish off the worksheet and do some textbook questions.